Welcome group. We're going to be looking at ways in which we can apply percentage composition. So at this point we know how to calculate the percentages of elements in a compound, and we want to see what the application is to chemistry. And just quickly flash this slide up here to show an example of a very useful instrument that chemists use, particularly when they're analyzing what happens when a compound is ionized and how it breaks up into different ions. However, it can also be used to determine for new compounds how heavy the molecule is. The sample is introduced as a gas, and in this example it's isobutane C4H10. The sample is ionized using more or less an electron gun. The charge is put onto the particle, and the particle is directed through this path, and a beam of ions is going to arrive at the detector and give a signal based on the abundance of that ion. The mass spectrograph, or mass spectrum, is for lighter fluid or butane, can be used to determine the molar mass of the chemical that was sampled. The molar mass is really just the mass of one molecule, except it's in grams per mole. And we need to know this information when we're calculating chemical formula for new compounds, because having just the elements present in the compound is not enough. We need to know the quantities, the number of atoms of each. So if butane had never been analyzed before and it was run through a mass spectrometer, chemists would know that the molar mass of butane is 58 grams per mole, and through other methods or other calculations, the percentage compositions, if they were known, the chemical formula of the compound could be determined. So the three things that are involved in this process for determining chemical formulas is determining first the percentage composition. Percentage composition, we already know, is percent abundance by mass of each element, and it can be found experimentally by measuring masses of reactants and products. I'm going to show you a little clip here of an instrument in operation called a combustion analyzer, and this little animation is going to help you understand how the percentages of hydrogen and carbon, at least in a hydrocarbon, could be determined by burning the sample. Let's have a look.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
All right, as we saw, this instrument captures the different components, the different oxides. The water is the oxide of hydrogen, and the CO2 is the oxide of carbon. So for a substance that contains only carbon and hydrogen, this could be done to at least determine the mass percentages of those two elements. And if the compound had other elements besides carbon and hydrogen, this combustion analyzer instrument could still be used. However, we wouldn't be able to determine the percentages of all the elements unless indirectly, if there were three elements, for example, we could probably determine the percentage of oxygen if we knew the percentage of carbon and hydrogen. If there were more than three elements, we would only be able to determine, again, those two. Now, going back here, we know what percentage of composition is. The empirical formula needs to be defined. The empirical formula is the simplest whole number ratio of the combining elements, whether they be atoms or ions, and it can be found from mole ratios. An example of an empirical formula for an ionic compound, that's all we use. That is, for the formula unit, calcium carbonate would have an empirical formula of CaCO3. We wouldn't call that a molecular formula because ionic compounds don't exist as molecules. And we know that the formula unit represents the lowest ratio of ions in that ionic solid or in that ionic substance. Now, a molecular formula is slightly different. For a compound such as hydrogen peroxide we looked at before, that is a molecular formula. It provides the actual numbers of atoms. There are two hydrogen atoms, there are two uh, oxygen atoms, there are four atoms in total. So the actual molecule has four atoms, two of each. The empirical formula of that compound would be the lowest ratio of atoms, HO. It doesn't represent the actual particle, it represents the lowest ratio in that there is one hydrogen for every one oxygen. An empirical formula is a useful formula in that it does give us that ratio of elements, but it's not as useful as the molecular formula because it doesn't actually describe the number of particles in a unit. Okay, so ionic compounds only use empirical formulas, and molecular compounds will use molecular formula, and where the ratio of elements can be reduced, the empirical formula may be different. When we look at, for example, water, which has three atoms, two of hydrogen, one of oxygen, the empirical formula for that would also be H2O because there's no simpler ratio than 2 to 1. So we'll find that sometimes a molecular formula can be reduced to produce a different empirical formula, sometimes it can't. Let's look at an example of a calculation showing the whole process of how we determine a molecular formula for a compound. All right, we'll get started with glucose as an example. The process of determining a molecular formula is pretty involved, so you just want to make sure that as we go step by step, that you understand each individual part, and with practice you'll be able to put together all of the separate pieces. So the first stage, assuming we don't know the chemical formula for glucose, we don't know its molecular formula, would be to determine its percentage composition. So a combustion analyzer, run the sample, the carbon and the water trap and the carbon dioxide traps will give us the percentages of carbon and hydrogen um, from the original mass of the sample. The percentage of oxygen can be determined by subtracting those from 100. So theoretically, if this was run through a combustion analyzer, we would expect to see about 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Those three percentages should total to 100. The next step is looking at 100 grams of the sample. Now this is probably the easiest mass to assume, because if we assume 1 mole, we're going to have to determine uh, the number of moles of each of the elements, and it's not so direct from percentage composition. Percentage composition is by mass, so if we assume 100 grams, it naturally just goes into a mass. 40% carbon is going to be 40 grams out of 100, 6.7% hydrogen will be 6.7 grams out of that 100, and the remaining 53.3% would be the other 53.3 grams. So now we have a mass to work with. This may not have been the mass that was analyzed, but that doesn't matter. Those percentages allow us to use the law of constant composition, is that those percentages will hold up regardless of the mass that's used. So if we assumed 1,000 grams, we'd have different masses, but they would be in a ratio according to the percent by the elements. So now what we can do, because we know these elements and we know their mass is in 100 grams, is we can calculate the molar composition in that 100 gram sample. So what we're going to be looking at here is the calculation of the moles of each of the elements, and we're going to be comparing them in a ratio. We want to determine in this process, after percentage composition, which is step 1, the empirical formula, which will give us the simplest whole number ratio of the elements. And now this is a ratio of moles that we're really after. We've determined a ratio of mass. We've looked at the combustion analyzer data. We've found the ratio by mass. However, now to come up with an empirical formula which gives you the number of atoms of each of the element, not the weights, but the number of atoms, how many carbon atoms, how many hydrogens, how many oxygens, and the lowest ratio, we need to go to moles. Atoms can be compared by ratio in an empirical formula, and that same ratio would hold up on a molar scale. Does not hold up on a gram scale. We can't go from these numbers here to suddenly concluding that there's about C40, H7, O53 if we were to round those to the whole number. The mass ratios do not translate into the ratios of atoms because obviously carbon, oxygen, and hydrogen have different um, atomic masses. So we go to moles, and that allows us to compare on an equal scale. So to go to moles, we just need to know the molar mass of those elements. We divide mass by molar mass, so we're using our formula number of moles equals little m divided by big M molar mass. So for each element, we calculate the number of moles from that 100-gram sample, and we get now 3.33 moles of carbon, same number of moles of oxygen, and double that of hydrogen. Now as a ratio, that wouldn't be convenient to leave in that form, but as a lowest ratio, we could say that the empirical formula for that compound going to lowest terms would be 1 to 2 to 1. And so the easiest thing when we come up with this mole ratio in this step right here is to simply divide all values by the lowest number. Or I'll say lowest factor. Sometimes we may want to go with a factor that's smaller than the lowest number if we find that they're not all divisible by that value. In this case, 6.66 was divisible by 3.33. So that was easy. So the empirical formula is about 1 to 2 to 1 exactly for moles. So it's going to be exactly that number for atoms, whether we consider on a molecular scale or a molar scale, it will hold up. Now what we're not saying here is we're not saying that glucose is 4 atoms, 1 carbon, 1 oxygen, and 2 hydrogens. We're just saying that the lowest ratio of atoms is 1 to 2 to 1. To get the molecular formula, we first need to know, okay, how heavy would this empirical unit be? How heavy is CH2O? Well, 1 unit of CH2O would have an atomic mass, a relative atomic mass of 30.03 units. Or we could say that a mole of those units would have a molar mass of 30.03 grams per mole. Now, even though glucose is not CH2O, its empirical formula is going to be a fraction of the actual molecular formula. And that fraction will tell us how to adjust the number of atoms in the molecule. So we'll find that from the mass spectrum, the heaviest ion will give us the mass of 1 mole. The molar mass will be the mass of that heaviest particle before it starts to break down as it goes through the instrument. So as we go to that mass spectrum and determine that in fact glucose has a molecular mass, or actually in atomic mass units is fine, but in grams per mole it would be on a molar scale. Glucose, a mole of glucose would have a mass of 180.15 grams per mole. We're now able to see that the actual molecule has a molar mass which is 6 times heavier than the empirical formula molecular mass. And because of that, we need to adjust the coefficients for the empirical formula to come up with our molecular formula. And it would just be a simple matter of we would need 6 times as many of all of those elements. And that would give us 6 times as much mass. So the actual subscripts are not 1 to 2 to 1, it would be 6 to 12 to 6. It's still in that ratio of 1 to 2 to 1, but this molecular formula now represents the actual molecule of glucose, and it's a match to the molar mass of the compound. So percentage composition leads to mass ratios for a specific amount. 100 grams is a convenient amount. Molar ratio from that allows us to come up with an atom ratio. The mass of one unit of the empirical formula is compared to the actual molecular mass, and any adjustments are made. Okay, for the flowchart number 6, I just modified this question a little bit from the textbook. Instead of solving it out, I'm just going to do a flowchart. And the first step in our flowchart, which allows us to determine the empirical formula, is to determine the mass of the other fraction. So the 26.80 gram total mass is 4.90 grams of hydrogen. The remainder would be carbon. From there, we can determine the number of moles of both hydrogen and carbon, and that would require us to divide our mass of an element divided by the molar mass of the element, which is 1.01 and 12.01 respectively. So we could just take our element masses and divide by the molar mass of the element. In this case, that would give us 2 mole values, which can then be compared. So step 1, step 2 involves sort of 2 parts to it. Step 3 would be compare NH to NC as a ratio and reduce it to lowest terms. The last step would be to write the empirical formula using the lowest ratio as our subscript amounts. So whatever that would be, we can say a ratio in step 3 would be x to y. I guess my order here is actually a little different. If we were comparing moles of hydrogen to moles of carbon, then we would actually want a ratio. If we said moles of hydrogen to moles of carbon, if that's whatever x to y, then our chemical formula would be CY HX. So the question really is, what are those numbers? All right, number 15, I've already started the solution for you. The first step in the process, since we have our percentage compositions, would be to take that 100 gram mass. Let's assume it's exactly 100 grams to 3 significant digits. So we have 1.00 times 10 to the exponent 2 grams. That gives us exactly 79.8 and 20.2 grams. Those masses of carbon and hydrogen can be converted into moles. We're using the molar mass of each element. Just a comment here, hydrogen's diatomic, but we don't consider that here. When we're trying to determine the moles of hydrogen, we're talking about moles of hydrogen atoms. So the molar mass that we're using here is for the atom. Molar mass for carbon is for the atom. Anything else would be specifically indicated. So here, converting these masses into moles, we can now, from those calculations, make comparison of the molar amounts. The values here are going to be, I'll just put an approximate molar mass of 12.01 grams per mole, and we're looking at 70.98 grams. So when we evaluate the math on that, we get about 6.644 moles of the element carbon in that 100 grams. We can't subtract that from 100. We're not working with masses anymore, so we have to calculate both of these directly. The number of moles of hydrogen would be 20.2 grams, and we know that every mole of hydrogen has a mass of about 1.01 grams per mole. So we're looking at exactly 20 moles to 3 significant digits. I can carry an extra 0 here, just remind myself that that was exact actually. Okay, so that is 20.00 moles. Now I take the ratio of those, and here if we divide both by the lowest number, actually this does work out. We do get a lowest ratio because 20 is divisible by 6.64, and sometimes the math would suggest that it's not exactly a whole number ratio, but considering that we've made sort of approximations in the molar mass of the elements, that can account for a slight discrepancy in this ratio. So when we compare moles of carbon to moles of hydrogen, we're going to get 6.644 to 20.00, and that's approximately 1 to 3. That tells us that our empirical formula there is going to be 1 part carbon to 3 parts hydrogen, looking at parts being an atom. So empirical formula would be CH3. Now, that's not the actual formula for the compound ethane. Knowing that it's the molar mass of CH3 would be 12.01 plus 3 multiples of 1.01, which would be 15.04. Then we're going to get grams per mole for the empirical formula of 15.04, and the actual is 30.1. So the molar mass of the molecular formula is 30.1, and that's approximately twice the molar mass of the empirical formula. That tells us that our empirical formula is off by a factor of 2, so therefore we need twice as many atoms of both elements. The compound's molecular formula is C2H6. Okay, so we're just comparing. So we're just comparing CH3 in the lowest terms ratio to C2H6, which is the actual, and we're able to determine the final chemical formula for the compound. All right, well, tomorrow in class and over the next couple days, we'll be working on making sure that this process, which is a little bit involved, something that we can do as groups. And in your groups that have been assigned to you, you'll be going through one of 2 questions to determine the answer. But first of the flow chart will be done to outline the steps, and then executing it with the math will be the follow-up. Summary of how to calculate a molecular formula from empirical formula and measured molar mass. Well, from empirical formula, if that work has already been done for us, then we're calculating the molar mass of the compound, and we're comparing that to the actual molar mass derived from the mass spectrometer. Okay, so we need to know that. If the measured molar mass has been given, then it's just a simple ratio of the two that allows us to make adjustments to those subscripts. We may have to increase the subscripts. You'll never have to decrease the subscripts, but because your empirical formula is as low as the ratio can be. If the percentage of composition is given, on the other hand, and the measured molar mass is provided, we can follow through the process that's already been modeled for you. Assuming 100 grams is the method that we used instead of assume 1 mole. We assumed 100 grams. We calculated the mass of each element in that 100 grams sample, and we used the molar mass of the elements instead of the molar mass of the compound. If you're looking at number 1, it's a little bit different. if you want to follow this method, if it makes sense to you, and some students find it does, look at uh, the sample problem in your textbook on page 192, sample problem 3, and that's the method that they use. They assume 1 mole, and they follow it through from there. The end result is the same. The mole ratio of elements needs to be compared, um, and once that's done, the empirical formula is obtained from 100 grams. The advantage to this method, which is outlined here, is that you are already assuming 1 mole of the compound. So the ratios that you get will be uh, very, very close to the whole number values of the molecular formula, not the empirical formula. So it bypasses one step. I prefer the assuming 100 grams, a little bit more methodical. The math ends up being a little shorter with the other methods. You look at both. If you're looking for a shorter strategy, then you can apply that one. Otherwise, you can just follow the ones that have been modeled for you. Sample problems are often good to go to see other questions that have not been modeled in the video lessons. So again, here in class, we're going to be working through some questions with partners or with inner groups, and then independently working on some questions on pages 196, 197. And at some point, we'll want to look at the big picture and see that we can put all these steps in order, and that'll be part of our review in class tomorrow. So I'll see you then.